Welcome to Learning Chemistry with Faye. In this video, we will learn the solubility characteristics of compounds, and we'll also learn how to write net ionic equations for chemical reactions. Let's first take a look at the solubility rules and what is actually a chemical reaction. Let's first look at chemical reactions. We can usually detect the chemical reactions through different traits, and we can observe their changes that usually indicates a chemical reaction has occurred. For example, color changes of states. For example, when two compounds react with each other, sometimes they would precipitate or create gas bubbles. Temperature change, pressure change in a closed container. If it has a closed environment, it can change pressure, and also change in odor. Let's take a look at a couple examples of how the solubilities plays in a part of a reaction, of chemical reactions. The first one is copper nitrate in water. So what we're looking at here, copper nitrate has the chemical formula of copper, which is Cu, and nitrate, NO3, right? Copper 2 nitrate means copper has the charge of oxidation format of 2, right? So nitrate has a -1, so therefore you need 2 nitrates to balance out a single copper, right? So after you put copper nitrate inside water, it turning into this blue liquid, and it's all homogeneous, it's all well mixed, and it turning into this liquid that you can't really distinct anything uneven or have different parts of it in the solution. So this particular compound is called soluble in water. And let's look at another example, calcium carbonate. Calcium carbonate is the CaCO3, where the calcium has the charge of a +2, while carbonate has a charge of -2. And in this particular compound, if you put it into the water, it actually creates this white, very visible white solid. So therefore, it is actually not soluble, and it precipitates right out of the water, and it's visible, right? How do we recognize all the compounds whenever they are soluble or insoluble in water? There are patterns. So from this table, which is called solubility rules, the left-hand side shows the solubility characteristics in general of particular ions in compounds. Okay, so for example, at the top part, if you have these ions in compounds, they are generally soluble in water. And at the bottom, it shows if you have these particular ions in a compound, they're generally insoluble. However, everything comes with exceptions. And on the right-hand side, if the left-hand side ions is coupled with the left-hand side ions, then that means that particular compound is the opposite of what is said. Okay, so for example, at the top, if we have chloride, bromide, or iodine ions, they are generally soluble. However, if coupled with silver, mercury, or lead, then they are no longer soluble. And then let's look at the bottom. We have carbonate, chromate, phosphate. They're generally insoluble in water unless they're coupled with barium, ammonium. So memorize these will take you really far in chemistry, but at least learn to recognize them, especially the polyatomic ions. Let's take a look at a few examples using this table that we have just learned. So first is the potassium sulfate. So what we will do, we'll first try to locate where is potassium, and then we see it in the solubility compounds at the left-hand side of the table at the top, right? So now we need to look if the right-hand side of that particular compound sulfate is in our exception. Since it's not, then we can conclude that this particular compound is soluble. And we continue down the line and do the same for the rest of it. So now we look at ammonium, and ammonium is soluble, and sulfur is not part of the exception. Therefore, this particular compound is also soluble. And in the next one, we can look at barium is insoluble, right? Barium coupled with sulfate is insoluble. Since we found the right-hand side sulfate at the top left table, that says sulfate is a soluble ion unless it's met with one of the exceptions on the right-hand side, which it says barium is one of them. Therefore, this particular ion is not soluble. And let's look at the last one. So you can find phosphate at the bottom, which it says insoluble compounds, and this is a part of insoluble. And if you look at the exceptions, copper is not part of the exceptions. That means that this compound is not soluble. After we learn solubility characteristics of these compounds, let's take a look at what happens in a reaction. So in this example, we have lead nitrate and potassium iodide. And the picture below shows the clear liquids of each compound. Okay, so one of them is labeled potassium iodide and the other one is labeled in the molecular bubble, that's the lead nitrate. So if you look at the two containers in the picture, they just look like a clear liquid. They almost look like water-like, right? They're not really distinctible from each other. However, what happens when we mix them together? When we mix them together, some of these ions or all these ions will start break apart and they will change. They will mix and change in a different reaction. In a reaction. And then in here, the reaction has formed a solid and it precipitates out the water. There are also other ions dissolved in the water which are homogenized in the solution, but only the ion, the free ions that's flowing and dissolved inside the water will do that. The precipitates will not be homogenized and mixed into the water because it is not soluble. So let's take a look at what happened next. And here you can clearly see a separation between the solids and the liquid. And that is what it looks like after the two solutions has mixed together. And let's look at what actually did they produce. In the solution, what occurred is the lead nitrate and the potassium iodide had exchanged their cations and anions and formed lead iodide and potassium nitrate. So over here, you wanted to be careful whenever you are switching the ions. You want to make sure their charges, the cations and anion charges, are balanced within each compound. Okay, so you don't want to have PBI versus PBI2. And once you form both of these, the lead iodide are actually the substance that had precipitated out of the liquid. And the rest of it, the potassium nitrate, stayed in a ion form inside, dissolved in the liquid. So this is the reaction. And then once we had completely finished writing the reaction, make sure your products are correct. And then we want to balance the chemical equation. So this format of reaction is called the precipitation reaction. Here we further taking the compounds and put them in the cartoon format to represent what they look like in the liquid form. So this is the compounds in their individual glass with the cations and anions as ions dissolved in the liquid. Recall in the previous slide, whenever they were in separate beakers contained in separate containers, they are both clear water-looking liquids. But what happens when we put them together? These cations and anions, they rearrange themselves and they cross-react, cross-bond with each other. So remember, these ions, only the precipitates forms solid bonds. The rest of the ions, they're called floating ions. So they just kind of float around, but they are sometimes kind of, format of a couple, right? Because they're positively and negatively charged and they're attracted to each other, but they are not an actual bonded compound, but they are attracted together like ionic compounds. Okay, so only the lead iodide, which forms a solid, forms actual bonds. And in this case, we can see the exchange has happened. And here is our solution with our new compounds, with our new products. And this is what the final solution looks like, with the lead iodide at the bottom of the solution and with potassium and nitrate floating and dissolved floating inside the solution. Okay, so remember that yellow solids precipitates out of the solution, that is the lead iodide. After we have learned the chemistry behind the scenes of these reactions, now let's take a look at how do we actually put them in a equation format. So what you're currently looking at, this is called the chemical equation. We write down simply everything that we included in the solution except water, except your solvent, which in this case is lead nitrate and potassium iodide, right? So, and then what had happened, we write an arrow, not equal sign, to the product. Remember, they're not equal. The compounds have all changed, right? So you have formed the lead iodide with the 2 potassium nitrate. But in reality, as you remember, the potassium nitrate, they're floating ions. They didn't really precipitate and they didn't really actually participate in the reaction. They just kind of float around. So how do we write that as well? So we separate all the ions. Remember, you keep the solids together. You don't separate the solids, but you keep the solids together, and we separate all the ions and write an overall ionic equation. So we write everything, we separate all the ions, and we call this the ionic equation. So in this particular equation, we still have everything in there. We just separated everything into ions that could possibly be separated except the solids. Remember, solids stays in the compound form because they're not ions. They actually form an actual bond, right? So, and then what we do is we want to cross off the ions that is floating in our solution, but they actually don't form precipitation. Okay, so they are called spectator ions. So on your in your equation, where you can display it as, you can write them down, you can label them, you can simply put a box around them or underline them. They're all acceptable. Just make sure you actually label them somehow to basically distinguish these are the spectator ions, and the rest of it are the actual ionic equation. So we crossed these spectator ions out of our overall ionic equation, then they gave us the net ionic equation. And that is our final reaction. Now we have learned all 3 forms of the reactions, how to write them in the equation format. Let's take a look at an example. Okay, so in this particular question, we are going to practice how to write all three forms of equation. The first one, we're going to do a chemical equation. The second one, we're going to write a overall ionic equation, and then we're going to reduce it to the final net ionic equation. Okay, so in this equation, we're going to we are going to write the reaction of silver nitrate and sodium phosphate. Whenever we want to write all the equations to represent this reaction, we always start with a balanced chemical equation. So in this case, we're going to start with the silver 1 nitrate. Remember the number in the Roman numeral format inside the parenthesis in your compound name represents the oxidation number, which is the charge of your silver. Do not confuse it with a quantity. Okay, so we know that silver 1, that means we have silver with a plus, and we know that nitrate has a charge of -1. So therefore, we only need 1 silver and 1 nitrate. So we will have silver nitrate. Okay, so it's AgNO3 with our sodium phosphate. Phosphate is a polymer, therefore it has a charge of -3. And sodium, as we remember, is in the first column of our periodic table and is never an exception that only has a charge of +1. So in this case, we're going to need 3 of our sodiums to balance out 1 phosphate. And it's going to form, remember, now we're going to crisscross the cations with its anions to form silver phosphate and sodium nitrate. And here you can see we have labeled silver phosphate with a S. That means that this is actually our precipitate. This is a solid. So therefore, whenever we carry it into the ionic equation format, we don't separate this particular compound. But how do we recognize which of these compounds, which of these products is the solid? You want to use your solubility rule to make sure your solids is a precipitate. It also doesn't dissolve in water, okay? And then another rule of thumb, not always true, but generally the transition metals likes to precipitate more than others. Not always the case, there are plenty of exceptions, but generally your transition metal is the precipitation, okay? Okay, now we're going to expand our ions. Oh, we're actually going to balance the chemical equation. So now we're going to put 3 silver nitrate with 3 sodium nitrate, and this way we can balance with all the silver, correct quantity of the silver and nitrate. Remember, if you wanted to have multiples of your polyatomic ions, for example, your nitrate or phosphate, you want to put a parenthesis over the entire PO4 and then put the quantity. You don't want to just leave out the P or write a PO42 or PO43. So therefore, it would be very confusing for you to read to know that 3, does it just represent the oxygen, or was it the phosphate, or was it even the sodium phosphate? Okay, so just make sure that whenever you want to write multiples of your polyatomic ions, you wanted to write the parentheses of the entire ion. Just that ion, not the whole compound, but the ion. Whenever you wanted to label the quantities of the entire compound, you put it at the front of the compound. Okay, so now let's write the expanded reaction, which is our expanded ionic equation. Okay, so remember, whenever we're carrying the quantity, the numbers into our ions, whenever we separate our cations and anions, the quantity of the 3 carries, or whatever number that is, carries with our cation and ions, and anions. So in this case, we have 3 silver, 3 silver and 3 nitrate, right? And then we're going to have 3 sodium with 1 phosphate, right? So with just 1 PO4 negative. And it's going to give us our solids, which does not separate, just stay as in place. And then we're going to have another 3 sodium with a 3 nitrate. So now we have a balanced ionic equation. And now we can go ahead and cross off all our spectator ions. And what is left in this equation are going to be the answer of our net ionic equation. So whenever you are writing these equations, it's almost intuitive for your teachers or professors to know that whenever you cross something out, that's how you label your spectator ions. Okay, so this is how we recognize and how we write a chemical equation, a full ionic equation, and a net ionic equation. I hope you have learned a lot, and please go ahead and subscribe to make sure you don't miss any videos. And if you wanted to let me know that you have learned a lot, go ahead and like the video, and I will see you in the next one.